Okay, thank you, Heather, for the very nice introduction. And it's my great honor to have the opportunity to discuss the new release of RP 12.4 from IEST. And from the architectural components like wall, ceiling, floor, all these are going to generate particles. So one is reduction. The other is isolation and then removal. Now, if the contaminants is escape into the room, then the room concentration has to be reduced through the dilution of filtered supply air. So if you cannot contain, then you have to dilute. So that's the typical strategy for the source control. Transmission is you keep the distance from the contaminant source, so the impact from the contamination will be less to the critical process. The other is the airflow cascade. You want to make sure upstream, midstream, downstream, and from clean, less clean to dirty. So in a cascading airflow relationship. Migration control basically is the control the contaminant migration into the clean room. So pressurization or depressurization is typically the way to do. The other is what we call the airlock. Pressurization is good for static control when all doors close. Airlock control is that for the dynamic control. Since you have a door, you're going to have traffic for people, for material, for products. So you had to open the door. Every time you open the door, there is a chance of a particle migration because the delta P, the pressurization you created earlier when the door is closed, is no longer exists, or the pressure level could be minimum to prevent particle migration. So, so these are very key concepts regarding the design consideration. So now let's move back to the 12.4. What are the information that this 12.4 is going to cover? And we have 6 sessions. And session 4, 5, 6, these are the key elements of this document. And we have many figures and tables and appendixes. And what are the new information that we include from the previous edition? One is the room pressure criteria, strategy, and impact to building pressurization, and the enclosure air tightness, and the relationship to room pressure control, and airlock category, flow diagram, and applications. And the clean room entry and exit protocols, and personnel grounding plan, and ESD tester, and grounding connection to many items. So I'm not going to read through these, but these are the new information that we included in this document. And also airflow turn down and reset strategy and demand airflow control. This is to reflect the new ISO Part 4 and Part 16 standard. And also a new terminology called contaminant removal effectiveness, CRE, and this concept or this terminology being introduced into the new ISO Part 4 and Part 16 standards, and which use as a correctional factor, which can increase the predictability in estimation and the calculation of clean room airflow rate. And also we had many articles, books as a references. And also we did some improvement and enhancement. One is the integrity of a building envelope and interstitial space to prevent the insect paths entry, process flow pattern, wireless sensor, and dedicated space for storing cleaning equipment, design for facility disinfection, CFD. And so let's look the section 4. And we have lots of information included in section 4. Mission statement, goal, strategy, collection, and analysis of effects. Alternation of an existing facility, or called a renovation of an existing facility. Energy efficiency, ergonomics, constructability, determination of the needs. And in section 5, we have airflow pattern, airflow guideline, air filtration, HVAC system configuration, temperature control, humidity dew point control, pressure control. We had a lot of new information in the pressure control category. exhaust design, AMC consideration, microorganism, noise, vibration, electrical power, backup power, electrostatic interference, grounding system, lighting, life safety system, mini environments, some advantages and disadvantages. Factory automation, facility monitoring, decommissioning, airflow turn-down reset, and a demand-based airflow control. So lots of new information included. And section 6 basically is the pre-construction planning, implementation of protocol program. And in appendix, we have reviewing and testing concepts, level 1, 2, 3, 4, Cleanroom protocol, Cleanroom modeling approach. Modeling basically is the mathematical approach to estimate airflow rate. And we have a sample for the air change rate comparison between recommended values versus the surveyed in ISO classified Cleanroom category. And also we have a table regarding what are the contaminants, what category of their effects, and value of a magnitude, example, and remedies. For example, particle, you have multiple categories: chemical, mechanical, electrical, biological, microbial, chemical, and a molecular, chemical, mechanical, energy level, EMC, EMI, RFI, temperature, humidity, light, intensity, wavelength, and sound, vibration. So we have all information included. I didn't copy all the information, but just show you the structure of this table. So in the real document, RP-12.4, you will see all this detailed information for the examples and remedies. And redundancy, 5 levels of the redundancy. And so this can provide a detailed information for design engineer as well as the operational engineer to set up proper documents for their facility operation. And also we include an example for energy consumption in Cleanroom. For example, this facility 2, Cleanroom fans utilize 27% of all energy consumed. And so it's a big chunk of the energy consumption for the Cleanroom facilities. And of course, you have many other examples. Each of these could have a different percentage for each specific facility, but this is a good illustration and to encourage other people to do their energy consumption analysis in their own facility. And also key considerations for the design: process, heat load, contamination control, recirculation air system, makeup and exhaust system, chill water, cooling tower water system, electrical, and control systems. So each of these category have lots of sub-consideration and in detail concept and actions. Since this is the introduction, I'm not going to go to the detail level of each specific concept. This seminar is to serve as an introduction to encourage the readers or the viewers to engage with the working group 12, and also to purchase this new standard for their design purpose and for their construction project. There are several typical AHU configuration that we include in this standard. One is a very typical low-end clean room, which is heating, cooling dominate, very similar as the commercial space, except you put a HEPA filter at the ceiling level. So you have a AHU provide a supply air through the HEPA filter to the clean rooms. Then you have a return air. You have a process exhaust. So this concluded the airflow loop and airflow balance for the simple configuration as this. Usually this is for ISO class 9, class A. And if you go level higher, 7, 6, 5, you may end up with primary and secondary system. You have a makeup air. You draw the outdoor air. Provide heating, cooling, filtration. Then you pump the treated air into the recirculation loop. So recirculation loop, you can have the big recirculation fans or fan filter units. Then you can provide a filtered clean air into a clean room, and you can return portion of air for recirculation, and you can return the rest of air and mix with outdoor air to be treated by the AHU and for outside air requirement for heating, cooling. And so typically for this kind of configuration, the recirculation flow rate is much higher than the makeup AHU. So you can create a high air change rate inside clean room, but your heating, cooling low, and the outside air intake for ventilation, for pressurization, or process air offset could be relatively limited, but you do need to have a high air change rate. So using this primary and secondary system, you can create a high air change rate and also provide a proper level of heating, cooling, and ventilation, and of course, pressurization. If you go to one level higher, this typically for ISO 123 level, you may end up with a primary, secondary, and a tertiary system. So this is once again is recirculation, provide ultra high air change rate inside the clean room, and a makeup air to all the outside air, and they provide air to the secondary recirculation AHU, and the return air you can mix with the recirculation fan system, or you can mix with the secondary recirculation AHU. The reason we have two AHU is this AHU, makeup AHU, basically is to treat the outside air, especially during the cooling summer, winter season. So outside air makeup AHU will take a lot of heating, cooling load to treat the outside air. This recirculation AHU basically is to handle the heating or cooling requirements inside the clean room. You have people, you generate heat, you have process, you generate heat. So you need to do a temperature control and sometimes the humidity control. And so this recirculation AHU will handle that portion of the responsibilities. So I'm not going to go to the detail, but this is just to illustrate that we have some information, valuable information, included in this standard. New addition we added is the airlock. There are 4 categories: cascading. Clean room has a highest pressure than the airlock, than the corridor. So when airflow from inside to airlock to the hallway. Bubble is that the airlock has a higher pressure than the corridor, than the clean room. Sink is that the airlock has the lowest pressure, lower than corridor, lower than clean room. And a dual compartment is that you put a bubble and a sink airlock in series. So if you want to walk from in a hallway into the clean room, you need to walk through the first door, second door, and the third door. And if you want to exit, you walk through the 3 doors. Typically, airlock, non-ISO require very clearly in verbal language that will be a time delay requirement for the airlock doors. In other words, you cannot open the two doors simultaneously. You have to have a time delay. Now, in case of egress for emergency, of course, you can push through the door, push the button, or this door will open automatically for you. But this is for the emergency purpose. But in the regular procedure, no two doors can be open at the same time. Time delay will be required. And the time delay, how long to delay is based on what's the air change rate inside the airlock. The higher air change rate, the shorter of the waiting time. So basically, you want to theoretically replace the airlock air once before you open the second door. So in other words, if you have 60 air change per hour in airlock, once you open the first door, the chance is, because you lost the delta P across the airlock door, so contaminants in the hallway could migrate into the airlock. So when you close the airlock door, the contaminant is already there, already inside the airlock. But you cannot open the second door. You had to wait, let the air, the contaminated air inside the room to be fully replaced at least once, theoretically. There is a ventilation effect in this. Typically, you need to wait a little bit longer to be replaced once. So to replace once, then you open the second door, the chance is the contamination going to be much lower to migrate further into the clean room. So that's the basic concept. And now the new ISO standard -4 and -16 use the language called a time delay, and no door can be opened at the same time. And actually has done a lot of research. Detailed articles can be found in their publications. And another information we included is the pressurization strategies. Let's say if you want to pressurize a room, this is supply air, this is a return or exhaust air. You want to make sure the entering air, typically supply air, is more than the departing air. Typically is the return and exhaust air. So you have a positive offset. If you want to neutral, the pressure is similar as the surrounding, you want to make sure the incoming air is equivalent to the departing air. So supply air equivalent to departing air, there is no surplus or deficit. If you want to depressurize the room, you want to make sure the incoming air is less than the departing air. So they actively have a deficit in the room, so they will draw the leakage air from the surrounding adjacent space. That's the way to make the room in negative pressure in respect to the surrounding adjacent space. So I have a one-day seminar called a tutorial for IEST, talk about detailed information, how to handle this. And each of you are welcome to attend that the tutorial seminar. I believe we schedule in IEST 2024, so next spring, IEST conference. And another very important table, we call it the pressure differential criteria. So this table basically into the several category. Let's say if the clean room and the hallway is one class difference, let's say ISO 7 versus ISO 8, outside is ISO 8, inside ISO 7, you will need to have a 0.04, which is 10 Pascal minimum pressure differential. This is for door closed condition. So we call it static control. And when door in operation, because you would have one class difference, airlocks is not required because the particle migration could be minimum. And now if you have a two class difference, let's say ISO 6 versus ISO 8, you still need to have a 0.4 pressure differential, but airlock may be required. If you have a less than 30 times door operation a day, then the airlock may not be required, but you have more than 30 times a day, airlock will be required. So you will need to install a two-door airlock to replace the single door. So now you need to have a two-door airlocks versus a single door. that separate two areas, and the pressure differential each gap, you will need to have a 0.2 or 5 Pascal. So two doors, you end up with a 0.4 or 10 Pascal, and there will be a time delay requirement. But if you have 3 classes or more difference, let's say ISO 5 versus ISO 8 as an adjacent space, you still need to have a 0.4 as a minimum, but the airlock will be definitely required. And if a clean room surrounded by non-clean room area, non-classified area, you definitely need to have a airlock plus the delta P. So delta P is good for door close condition. When the door is open, there is no delta P, or delta P almost approach to 0. So they have no way to prevent a particle migration. Particle migrate from high concentration to low concentration. Once you lost the delta P as a driving force, particle will move based on the concentration difference. The tendency is move from high concentration to low concentration, and just like you drop a coffee in the fish tank, that's the phenomenon. And airlock is for dynamic control. We accept the fact every time you open the door, there will be particle migration, but that's okay. Once we have an airlock installed, we have a time delay, we have the door closer, all these kind of elements included, you can minimize the particle migration during door operation. And also IEST, the RP-12.4, including several modeling mathematical formulas to estimate the particle concentration, average particle concentration inside a clean room. So basically, let's say this is just one of the example. Airborne particle concentration is a function of multiple variables. One is the outdoor makeup concentration. If your clean room is located at the semi-rural area, of course, the outdoor air cleaner. But if you're in the middle of the industrial area, your outdoor air will be dirtier. So there is a little impact on that. And of course, the second is the air change rate. And third is the particle generation rate. Particle generation rate has been ignored for so long that people use the table method to determine the required air change rate, but they ignore the particle generation rate. And ASHRAE and other entity, they have done lots of research on that. And also the combined filter efficiency inside the AHU and the recirculation, typically they are in series connection. And since they have a filter, they have the efficiency. So these are the one of the variable as well. At the ceiling level, you have a HEPA filter. Of course, that efficiency also make a difference. And the other is the percentage of particle generated that some they return to the returns air pass, but that the rest could deposit on the exposed surface. So not all the particles inside the clean room will return through the return pass that you designate, not all. So it's based on how you design the return pass. And also the ratio of outside air inside the supply air. And so one of the key variables, of course, air change rate, the other is the particle generation rate. These are the two key variables. The others there we call the minor variables. They make some impact within certain levels, but the air change rate and the particle generation rate, well, these are the key variables. And also the new ISO standard included the CRE, contaminant removal effectiveness, as a correctional factor, because this equation or other equations, these are the theoretical basis. So they assume the room particle concentration is evenly distributed. but in fact, it's not evenly distributed, as we know. So the correctional factor is to count what's the capability to remove the contaminants from the clean room, so these contaminants will not deposit on the surface. And so there is a few things. One is the fine particles could suspend in the air for a certain period of time. In other words, particle can dance in the air for a long time before they settle down. Unlike the gas, unlike a tracer gas or other gas, they dissipate into the air much more quicker or evenly, but particles and they can dance in the air. If they are in the supply return air pass, they can be exit through the return pass. But if they are in a corner of the room, of the ceiling, the chance is they are going to flow in the eddy flow. Then they can suspend in the air for a long time. So when air hits physical obstructions, such as equipment, air can turn around and find a passage to exit through return grills. But the particle traveling along with the airstream could lose their momentum and be stopped, trapped, and deposit on the local surface or floor. Not all the particle can exit smoothly through return air. That's another topic related with the CFD topics, that not because if you have a larger clean room, you only put a very limited return points, the chance is a lot of particle will have a hard time to exit through the return points. So you need to have adequate return points and to allow all the particles, or at least the good portion of particle, to exit. This RP-12.4 also included a table called the contaminant removal effectiveness. If the effectiveness is 1, which is the ideal unidirectional flow, contaminants do fully mix with the room air, but are timely and fully removed by return or exhaust air. So these are ideal, but most clean rooms, they are not ideal. You have lots of equipment, process, human being as an obstruction for the flow of furniture. So if the effectiveness, let's say 0.7, that effective unidirectional, good removal of contaminants, and but contaminants are in turbulent mixing with the room air, good positioning of supply return air. But if the effectiveness is going lower, typical, let's say 0.3, poor unidirectional flow design, small portion of contaminants are removed, but most reside inside the clean room. But if 0, which means no particle generated in the clean room, is exit properly. They stay inside the room. But if you go to the other end, let's say the infinitive, which means full exhaust at the source of contamination or contaminants. In other words, you have a capture hood or capture canopy. Once you generate a particle, they fully remove. But that's theoretical. In practice, it never happened that way. And also, there are so many sources of contaminants. You cannot capture all of them. You just capture the major source. Some minor source, you had to let them to release into the air. So these are the entire table. Most of our research by ASHRAE or other European counterparts. So most of these effectiveness value is a range from 0.7 to 0.3 range. So most of the clean room, even you design the unidirectional, they are not fully unidirectional. Once you have equipment process, you have flow obstructions, flow will not be unidirectional at all. Only good unidirectional at the up level of the clean room, but at a low level, once you air contact with this obstruction, it becomes a turbulent or eddy flow or very confusing flow pattern. So this table inclusion is to encourage people, when you use a theoretical model, be careful you need to apply for the correctional factors. Otherwise, your estimate value may not reflect the real needs in your clean room. And also this standard including some new concept. One is what we call the turn down and the reset. In old days, especially for pharmaceutical under the FDA regulation, typically people design constant airflow year-round, 24/7, 365. Even during the evening and weekend, you do not have operation. But since most people are afraid that if you change the airflow, you need to do a validation, and air cleanliness may not be guaranteed, so it's better not to change it. So now the new ISO standard, Part 16 and Part 4 allow clean rooms to alter their airflow rate as long as they can validate or prove that they maintain the cleanliness as the class as they need. So the demand-based flow control technique aim at avoiding using the full flow while still to maintain air cleanliness during unoccupied mode. In other words, air cleanliness can be automatically maintained and only to use the airflow as needed without oversupplying. And the room particle sensors can generate a feedback signal to modulate air clean room flow rate automatically by using either variable speed drive or recirculation fan or multiple fan filter units with a ECM motor, electrical communicator motor. So many ways to modulate the flow rate based on the either a fixed time schedule or based on the real-time laser particle sensors, and but if only allowed, permissible. The other way, what we call the reset and the turn down, is consider a widened range of the temperature humidity when the clean room is at the rest or unoccupied state. When permissible, variable speed fan could be used to control air velocity and reduce the energy consumption. When setting back performance parameters, segregation, including physical barriers or positive clean room pressure, should be maintained to prevent egress of contamination from surrounding area into the clean room. So basically to prevent a particle migration from hallway into the clean room. So when people use the variable flow, one very complicated thing is once you change the airflow rate, the chance is you will not maintain the same delta P as you used to have during the design flow rate. So the strategy to handle that challenge, to tackle that challenge, is to maintain the same offset for each room. So in other words, if you lower the supply airflow rate, you also need to lower the return or exhaust flow rate to maintain the same data volume, airflow volume. Once you maintain the same, then you can maintain the previous data P, not just the room you look at it, but also the surrounding room. Clean room, we consider clean rooms, we consider clean rooms as a suite of the rooms, not just a single room for pressure control. Pressure control actually is a control of multiple rooms as a suite. So each of these rooms with a pressure control requirement, if you use a variable flow, you want to maintain the same offset. Once you turn on the supply flow rate, you want to make sure the departing airflow rate also need to be turned down to maintain the same. So that add a lot of complexity for the design engineers, but that's the trending that people have seen that in the US and also in Europe and also some part of Asia that people starting using the variable as long as the keyword is permissible. If you have FDA regulation that they do not allow you to do variable, then you cannot do it. But if you have a particle counters or particle sensors to validate that in 24/7, your ISO cleanliness class can be maintained within the specification, then this will provide you a very strong proof that the air cleanliness is being maintained, even you alter the airflow rates. So last 2 years, lots of new publication, let's say ASHRAE or other European institutions, lots of new articles have been published. You can do a search to see what's the current practice and the trending. But if you want to hear more detailed information, that IEST in the ASTEC conference next spring, I have a tutorial. I will be the speaker to provide a 4-day discussion with all the case study, sample, and more information on the design control and more detailed information. So that concludes my introduction for the new RP 12.4, and we have roughly about 15 minutes, and I'm ready to address the question that you may have.
Okay. So let me go ahead and I'll start reading some of the questions that we got into the chat box.
Yeah,
So,
could you put a check on the screen for me to read as well, if it's feasible? Let me click my chat box so I'm able to see some
you
questions.
should be able to.
Okay, yeah, and you can read it to me just to be sure.
Okay.
Yeah.
So guidelines don't say anything about the containment leak test as per ISO 14644-3. Can you provide guidance when this test is required as an EU GMP Annex 1 is listed as mandatory?
Yeah, this is the document for cleanroom design consideration. Is not for the performance testing like NEEP has been doing. NEEP, which I'm also the chairperson for their new standard to be published later part of this year, that they included the segregation test and also contamination contaminant leak test to match the ISO current new ISO standard -3.
All right, and next question. It says the tightest ISO 14644-1 spec is, class ISO 1 with less than 10 particles or 0.1 per M3. For nanotech, are tighter requirements needed, including for smaller particles like 10 nano, I believe NM is nano, or 3 nanoparticles, especially for semiconductors and EUV mask environments, or perhaps this is strictly a tool issue, so out of scope for clean rooms?
Mark, that's a very good question. And I believe very soon we are going to assemble a new contributor team for the 12.5. Going to take another 2-3 years. We are going to start this revision effort in ASTEC 2024. And so this could be a good topic that we can include in the new document. We do not have adequate information to cover into this document, but this will be the thing to do. Possibly additional research could be needed to validate and to identify some critical data in order to develop a guideline for the question that you're asking. And during COVID time, actually set up the epidemic task force, developed some guidelines regarding the minimization for the airborne aerosol infection. from people to people. And so lots of mask testing or question related. But at the process level inside the clean room facility, especially for the nano application, and more information and more discussion, possibly more research data testing data will be required to draft up a more solid guideline for that specific topic.
All right, thanks. I'll answer the next question about sharing the presentation. I'll go ahead and share the presentation with everyone. This is being recorded too, so for a limited amount of days, you'll be able to access this recording after the fact too, just to answer that next question. It says here, what is the impact of humidity on particle count results?
Very good question. Actually, about 8 years ago, I chaired a research team did some investigation on the particle counts and the particle migration for on the temperature and the humidity range. And our observation during that time was that the temperature range, as long as within a normal temperature range, let's say 68 or 65 to 72 range Fahrenheit, and the impact for the temperature variation on the particle counts seems very limited. We check the particle. We use a very fixed aerosol emission into clean room to simulate ISO, let's say ISO 3, 4, 5, until ISO 9. So we can control the aerosol emission at a very fixed, stable rate. Inside the clean room, there is no people, no other, just we solely use the aerosol emission. And so we can control how much particle we pump into the space, clean space. And then we change the temperature of the room. Of course, all this automatically use the cooling control, heating control. Let's say we start from 75 degrees, we change every 2 degrees, 75, 73, down 71, until I believe we did a 60, maybe 64, 65 degree. And then since we have the fixed aerosol emission rate into the space, and we monitor the particle concentration. Each room we have, let's say we put an 8 or even 1 dozen laser particle sensor real time. And we send all the data and we plot these curves, particle concentration on a screen. And then we have a mathematical calculation in operation in our sequence, in our program and in our algorithms. And then we have a real-time room average particle concentration that can be illustrated on the screen at the real time. And then we look at the 24 hours timestamp to see what's any variation when we change the temperature inside a space. What we found is that as long as the particle emission rate is stable, the room average particle concentration, the variation or change seems not very significant. I'm not saying none, but average particle concentration is kind of jumping around. But if you zoom in out for 24 hours, it still follows pretty much a constant or a consistent level without major surprise. Now, for the humidity change, that's slightly different. Let's say if we maintain at a 70 degree Fahrenheit, we change the humidity level from 25%, 30%, 35, 40, 45, up to, I believe we went up to 65%. We didn't go further high. What we found that there is some kind of impact on the room particle average concentration data. Since we put, let's say, 8 sensor or 12 sensor in the room with a human being, we get all this data remotely on a big computer screen, and then we plot this trend line. We humidity level change, we increase humidity level, and it's complicated. It's not like a particle concentration decrease when you increase humidity or increase with humidity. It's more like within certain humidity range, it seems, let's say, a little bit higher. On the other range, seems a little bit lower. So this is what we call undefined pattern. We use a algorithm, visual identification to see the trending. And so our conclusion is possibly we need to do more tests. But when the humidity level change step by step, moving from 25% up to 65, we found that the particle count, room average particle count readings is in an undefined pattern. So that's our observation many years ago. We haven't done any further tests in that topic, but it's worth to do further study by other parties as well. It's a very good question.
All right,
Thank you.
next question is regarding particles deposited on exposed surfaces. Is there a superior material to discourage deposition?
Okay, let me read one more time. Regarding particle deposit on explosives, where is the superior material to discourage deposition? Epoxy versus, typically, of course, epoxy, you have a very good, easy for cleaning, and most time is more leveled and flush and a certain durability if thick enough. The removal actually, well, of course, epoxy as our, you can use a thick commercial vinyl. Either of these is, if it's good for cleaning, that's okay. But the floor itself is not the reason for the particle deposition. Particle deposition is that your design of the return air path may not be adequate or may not be smooth enough. So the particle, they hit other objects, obstructions, and then they lost momentum. So they cannot travel further for the 10 feet away return grill. They cannot travel anymore, so they find a way to deposit. So typically exposed surface and a floor, equipment, furniture, tables, these are typical. The reason for this timely removal cleaning for the surface particles is that if you do not clean them timely, with a little small disruption or disturbance, this surface particle can resume to be airborne particles. So that's not a good part. So that's why in Cleanroom we have a cleaning protocol to maintain a regular cleaning requirement in order to timely remove this deposit particle, and so that's a good reason. So the flow material is that they carry these particles that need to be cleaned. So I think so far either the smooth surface vinyl and epoxy can provide a good floor base for your cleaning, but you may focus more on the adequate return and a smooth path as well.
All right, next question. This is kind of a multi-question. Are there changes to the design requirements in ISO 14644-1 regarding the location of the air returns? Are there approved mitigation strategies to achieve class 6 or 7 if air returns are located only in the ceiling?
Yeah, typically for the current ISO-1 14644-1, that's the definition of air cleanliness. On the -4, this is for design and construction. -16 is for the energy conservation, and the -3 is for testing. Typically, in the -4 and 16, there is some language in the return. There is a new paragraph, actually multiple paragraph, a new section or chapter specifically designated for CFD. So in that paragraph, there is some language on the proper return locations. So if you don't have lots of CFDs and a smoke test for visualization, you can see most of Cleanroom, as we have seen, that the return passage is not adequate. Because once again, particle exit is not the same as the return air exit. Return air carry particles. Air can exit, even they bump the obstruction many times, they find a way to go out. But particles, they may not go that smoothly. So for ISO 6.7 class, typically we use a low sidewall return. For some semiconductor facility, we even use a raised floor return. Now, raised floor return is more effective return passage because they're coming down. So the passage is much smooth, less obstruction, but of course there is a cost for that. You need to raise the floor, and only ISO 9 people use, especially in the US. We see people use a ceiling return. ISO 8, ISO 7, if a typical pharmaceutical a large facility, typically they still use a low sidewall return. Not commonly see as a ceiling return because once you have when you have a HEPA filtered air to flush, push it down, the goal is try to use clean air to dilute the contaminated air in the air. So if you have a quick return from ceiling to ceiling, the chance is your clean air not really reach down low enough to dilute the particle, to carry the particle up to the ceiling. So ceiling supply, ceiling return, you may have a lots of a clean air bypass. And a bypass may not be good for the particle exit, may be good, easy for air to exit, but may not be good for particle to exit. And you can do definitely smoke visualization to see if you generate the particles at the working height, let's say on a table, and you have a ceiling supply, ceiling return, the chance is you may not get a full benefit of the HEPA filtered supply air, it bypassed. And it may reach down some, but the goal in the clean rooms is not to let air out, but let a particle out. That's the way to lower the particle concentration to maintain the ISO class as needed. Otherwise, the particle concentration will keep moving up. If you do not have a proper return, we're moving up. Now the room is getting dirtier and dirtier. So maintain a dynamic balance. We call it equilibrium. Particle in, particle out, in a balance, so you can maintain the air cleanliness. If you keep generating the particles, but less particle coming out, the chance is your concentration will moving up. So hopefully answer the question regarding the ISO 6 and ISO 7 for the return.
Wei, do you have time to answer one more question?
Yeah.
I know we're at time, but I just saw this one question, I think. So it says, it appears that IEST now requires a minimum of 10 PA between rooms.
Is this in the chat box?
Yes.
Yeah, I'd like to move that one. Is it the very last one?
Let's do that one. Yeah, there's a couple more, but I could always send you the questions and we can email the answers back.
Yeah. So my screen is the last one, is IEST-RP-CC012.4 address dry room. Is that the one you?
No.
Oh.
So it says here, there's a minimum of 10 PA between rooms of one class difference. That IEST now requires. So ISO 14644-4 allows at least 5 PA. IEST seems to be more stringent. What should the users be aware regarding the difference between the IEST and ISO 14644-4?
Okay, let me move back. Okay, I think I'm seeing the question. It appears IEST now require a minimum of 10 Pascal between rooms, one class difference. ISO 4 allow at least 5. And yes, since I've been part of the ISO 4 for many years, -4 many years, we have lots of discussion and debate, especially between the US experts and the European counterparts. And so the language that we adopt into the -4 is the, I call it the consensus, or in other words, compromised, to meet the majority requirement. So we use the word at least 5, but they are not opposed you use more than 5. Because in old days, in the US typical practice, 1.4, which is a 0.05 inch, is a typical pressure differential. So now IEST and actually they use a minimum 10, and but the ISO -4 they use at least 5. So these two may not against each other. It is more like the minimum 5 by ISO, but more than that is more desire. So it's a compromise or consensus base. If you look at the research basis on the US side, it's clearly indicated that 10 Pascal minimum. But in the European counterpart, in their practice, their rooms, clean room could be more leakier. And in other words, the air tightness may not be so good during construction or sealing. So it's hard for them to control 10 Pascal or above. So as the result, they prefer to use a 5 Pascal as a minimum. So it's a compromised language in the ISO 4 in order to reach the consensus. So that's the background information. Hopefully I address your question.
Yeah, I know.
If you look at the IES, if you look at the ASHRAE Cleanroom Design Guide, they published the 2017. They also indicate the 10 Pascal is the minimum. However, they separate, like IEST table, they separate. Let me move back to that table. I think that was a good question. Yeah, let me move back to the table. Now, it's a very important non-IEST and actually they put a separate category. Airlock is for dynamic containment. Delta P is for door close containment strategy. And actually to most people, if the structure is tight enough, 0.4 or 10 Pascal is not difficult to achieve. The question is, airlock is more expensive because it takes space and reduce the traffic time. And so in this table and ASHRAE table, they put two different category. And so hopefully my feedback address your questions.
Yeah, thank you so much, Wei. I know we're past time, so what I'll do with the
I think there is some questions between the questions you ask and the question you just asked. There was a few other between possibly we. Thanks for the presentation.
I know we're over time, Wei. So what I'll do is I will email you those questions that were not answered, and then I'll have you answer those questions, and then I'll send it back over to the attendees.
Yeah, there is a very
yeah.
quick feedback. Just a second. See the NEBB. Yeah, the NEBB new standard CPD standard is in the final touch-up. It could be released by the end of the year. So be ready either by end of the year or beginning of next year, because this is going to be a NEBB NC standard, a combination of both. So have more procedures to follow, but it's in the final touch-up.
All right, thank you so much, Wei, for all the information you gave. And like he had said earlier, he is having a full day class. That the full day class is actually is in March, so it's March 5th. You can find the details on the IEST website of the content and when it's going to be in the location. Thank you so much, Wei. Thank you for everyone for attending, and we will get those questions answered and sent back to you guys. And like I said, this is being recorded, and you will have access after the fact for a limited time to go back and listen again if needed. But thanks everyone, and everyone have a good rest of their day. Thank you so much.
Thank you everyone for your time, and talk to you soon.